Welcome back everybody to another video lecture. This is Miss Simino, and tonight we're going to be talking about liquids, the properties of liquids, boiling point, and this is the second video in our States of Matter series. Some more formal objectives for this video include identifying factors that determine the physical properties of liquids, talking about what evaporation means in terms of kinetic energy, talking about the equilibrium that exists when we're talking about vapor pressure, and identifying conditions and the definition of boiling. So the first thing we need to talk about is what do liquids look like on the molecular level. So that's why we call this a model for liquids, like what do most liquids look like. So hopefully you guys know that liquid particles are always in constant motion. They can slide past each other, so they kind of have a less structured molecular model than solids would. We would say that they also can flow past each other. So we'll say that gases and liquids can both flow, where when we talk about solids motion, we talk about them vibrating. So here it does say, however, liquid particles are attracted to each other, whereas gases are not. So we'll see those intermolecular attractive forces between the liquid particles, and we won't see them between the gases. On this slide, we're talking a little bit more about that model of liquids. So we'll say here that liquids spin and vibrate. They contribute to the average kinetic energy. But one thing to know is that most particles do not have enough energy to escape into the gaseous state, and that's why they stay a liquid. They would have to overcome their intermolecular attractions with the other particles in order to turn into that gas phase. So as you take notes on the slide, really we're talking about the distance between the particles in a liquid versus in a gas. So it says the intermolecular attractions also reduce the amount of space between the particles of a liquid. So if we were drawing liquid particles, we're going to draw them pretty close to each other, whereas if we're drawing gas particles, we're going to draw them much further apart. So that drawing will tell us that liquids are more dense than gases. Also, increasing the pressure on liquid has hardly any effect on the volume. So we can increase the pressure, high pressure, trying to push those particles, but there's only so much space between each particle, and so it doesn't really make a big difference. Whereas if we had gases, and there's definitely a lot of space to push those particles closer to each other. Increasing the pressure will also have little effect on a solid. So remember when we draw those molecular models of liquids and solids, those particles are pretty close to each other, so increasing that pressure isn't going to push those particles any closer to each other. And since we're really not able to change the volume of a solid or a liquid, we would say that they're already considered condensed states of matter because they're condensed, they're as small volume as they're going to go. So I love this term, vaporization. It kind of reminds me of like sci-fi films, like when that person was vaporized. And so like when you hear that term used on those sci-fi videos, it really makes me think of like somebody getting hit with a laser and disappearing. But you guys should know that vaporization actually has a different meaning in real science as opposed to science fiction. So here we're going to talk about that vaporization is the conversion of a liquid to a gas or vapor. So remember, we can use these terms gas and vapor interchangeably. So a lot of times people say, oh, the process is evaporation, but evaporation is what occurs only at the surface. So anytime you have a particle going from a liquid to a gas phase, we're going to consider that vaporization. But if it's happening at the surface, then we would say that it's evaporation. So when this happens, this vaporization process, some of the particles break away and enter the gas or the vapor state, but only those with enough kinetic energy are able to do that. So on the last slide, we said that a particle needed to have enough kinetic energy to be vaporized or go through the evaporation process. And so this makes sense here, this first bullet point that says a liquid will also evaporate faster when heated. Remember, there's that relationship between temperature and kinetic energy. Temperature is the measurement of the kinetic energy of those particles. So increasing temperature is going to make those particles move faster or have higher kinetic energy. So it also says because the added heat increases, the average kinetic energy needed to overcome the attractive forces. But we like to talk about evaporation actually being as a cooling process. You think that evaporation happens more often when your temperature is increasing, but if you look at the particles that are still left over, it actually gives it a cooler average temperature. So on this slide, you're going to see some of my bad drawings, and I just want to talk to you about why evaporation would be considered a cooling process. So we're going to start off with a simple model here. So let's say I've got these 4 particles, and I've written the average kinetic energy or the temperature of each particle inside there. So you can clearly see we've got 90, 100, 90, and 92. So if you were to add these up, you would find that the total here would be 372 divided by 4, and that tells us the average kinetic energy or the temperature of these particles is 96. Okay, so what's happening here? Let's say this is water and we're in the Celsius temperature. So all of a sudden, let's say like this guy breaks free from these bonds and goes into the gas state. Now we're just left with these 3 particles here. So if we were to look up or to determine their average kinetic energy, of course, it would be 90 plus 90 plus 92. If you add them up and then divide it by 3, it works itself out to be like 90.6. So if we compare the average temperature of the particles initially, it was 96 degrees. After that one that had a high enough kinetic energy left, we're at 90.6 degrees, and so you can see that the temperature decreased after that one particle left. Hence, evaporation is considered a cooling process. So as we just said, the particles left behind have a lower average kinetic energy, thus the temperature decreases. Sorry, my iPad is about to die. So it says, similar to removing the fastest runner from a race, the remaining runners have a lower average speed. Evaporation helps keep our skin cooler on a hot day, and so that's why we're sweating, because we're really trying to get that heat outside of us. One of the activities we're going to be doing in class deals with vapor pressure. So vapor pressure goes along with evaporation. So evaporation of a liquid in a closed container is somewhat different than the evaporation in an open container. So when some of the particles do vaporize, they collide with the walls of the container, producing vapor pressure. We really haven't talked a lot about pressure, but remember it's measured in like the number of collisions or with each other or with the walls. So as those particles go ahead and go into the gas phase and collide, some of the particles will return to the liquid phase or condense again. So after a while, the number of particles evaporating will equal the number of particles condensing. The space above the liquid will now be saturated or filled with vapor or vapor gas particles. So we'll say that there's this dynamic equilibrium. And remember, dynamic means it's kind of going back and forth. While you might have the same number, there's some particles that are going into the gas phase while others are going into the liquid phase. And so we'll say that the rate of evaporation is equal to the rate of condensation. So the particles aren't just staying as a liquid, or they're not just staying as a gas, but the number of particles switching between the two phases are at equilibrium. So as I was saying on the last slide, it says note that there will still be particles that evaporate and condense, but there'll be no net change. Shockingly, again, if we increase the temperature of the contained liquid, the vapor pressure will increase because we'll have more energy available for those particles in the liquid to overcome those intermolecular forces and become gases. And since we have more particles as gases, we're going to have more collisions, so we're going to have more vapor pressure. So a quick term that I want you guys to get is volatile. So we like to use the term volatile when we're talking about liquids. It just means that they're going to go ahead and turn into that gas phase easier. So when we do the activity in class, we would say that one of the substances are going to be more volatile or easily changed into a gas. Just take a minute, go ahead and copy this slide down into your notes. If you have questions, go ahead and ask me in class. So we now know the rate of evaporation from an open container increases as heat is added. The heating allows larger number of particles at the liquid surface to overcome the attractive forces, and heating allows the average kinetic energy of all those particles to increase. So as we've said before, increasing the temperature increases that vapor pressure or the number of particles going into the gas phase. So this definition of boiling here you definitely want to know, and it's where our vapor pressure of the liquid is just equal to the external pressure of the liquid. And this is also important to know. Bubbles form throughout the liquid and rise to the surface and escape into the air. So we're not talking about evaporation here, we're really talking about through like the whole liquid, like through the middle of the bottom, they're just turning into the gas phase and they're moving to the top and escaping. Okay, so this next part is like a little bit complicated, but you definitely need to know the difference here. So since the boiling point is where the vapor pressure equals the external pressure, the boiling point changes if that external pressure changes. So that was our definition. So the normal boiling point, kind of another definition, is defined as the boiling point of a liquid at a pressure of 101.3 kilopascals, or we consider that to be its standard pressure. So we said that the boiling point happens when the pressure of the liquid is equal to the pressure of the external pressure. So we know that the normal boiling point of water is 100 degrees, but that's at sea level or at that 101.3 kilopascal pressure. However, in Denver, the boiling point of water is 95 degrees, but that's because Denver is at a higher altitude. It's 1,600 meters above sea level, and the average atmospheric pressure is about 85.3 kilopascals. So that means that there's less pressure there, so the boiling point doesn't have to be as high. And we'll see some pictures in a second that helps make more sense of this. So in pressure cookers, which reduce the cooking time while water boils above 100 degrees due to the increased pressure. Okay, so I like these pictures that we have going on here. So this first one, we have water and it's not boiling. And it's not boiling because you have this external pressure pressing down on this water. If you look at the temperature here, we said that at sea level, that the boiling point of water is 70 degrees. So we just don't have enough average kinetic energy to get this to start boiling. Okay. But if you look over here, we're at the 100 degrees that were needed. We're still at sea level. Now we have an equal pressure between our vapor pressure and our air pressure there. So that's why we have our normal boiling point here. But if you look here, it says atop Mount Everest. Well, look at this difference in pressure here. This is 34 kilopascals, so clearly a lot less pressure pressing down on the liquid. So it'll be easier for it to turn into the gas phase. So that's why at the top of Mount Everest, water can actually boil at 70 degrees, which is kind of cool. So if you were to cook like a cake or cupcakes, you might look on the box and see that there's these things called high altitude directions. My kids were actually baking a cake earlier today, and one of the things I noticed is they even had you add like more eggs and more flour and stuff like that. And that's just because you just have a little bit different cooking time at those higher altitudes. I have a friend who lives in Colorado, and she always had to follow these different directions when she was a kid. Usually it means that you're going to have a higher cooking temperature. Maybe you're going to cook the items for a little bit longer than you otherwise would. So a boiling point it's important to know about is when we use autoclaves. We actually have one of these back in the teacher prep room. It's a device that's used to sterilize medical instruments. So they have a high pressure, and so they're going to get the water to a higher boiling point, so they're going to be able to kill off things. We'll go ahead and we'll put like bacterial plates and stuff like that in there after we've made those petri dishes. Boiling is also considered a cooling process, much the same way that evaporation was, and that's because those particles with the highest kinetic energy are escaping first. Okay, so on this slide we're going to talk about like something easy and then something really hard to understand. So the first bullet point, it says turning down the source of external heat drops the liquid's temperature below the boiling point, which we can probably figure out. So if let's say you're just boiling some water on the stove, it's boiling, 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 you turn off the heat and it stops boiling. Shocker there. This next one is like a little more complicated to understand. So supplying more heat allows the particles to acquire enough kinetic energy to escape. The temperature does not go above the boiling point. The liquid only boils at a faster rate. So if you were actually to measure the temperature of water, you would find that it's going to go ahead and boil at about 100 degrees. But it's never going to be like 105 or 110 or get up to 120 even if you're boiling it for an hour. What ends up happening is when those particles get enough kinetic energy, they go ahead and they escape into that gas phase. And that's why, I don't know if you guys have ever done this at your house, but maybe you were cooking something on the stove and you let it cook for too long and you kind of boil out all the water. And we've talked about how you have that salt and stuff left over. But the idea there is that water never got above 100 degrees. It just, because all those particles exited into the gas phase. Okay, so this is our last slide for this video. please just go ahead, take a minute, look over these review questions, make sure that you can answer them. If you still have questions, make sure you guys ask me in class tomorrow.